Hey everybody, my name is Lucas Beeler. I am a principal architect in the office of the CTO at Hazelcast. We're based in the San Francisco Bay Area. I wasn't originally supposed to give this talk. One of my colleagues was, but unfortunately he had a bit of a travel snafu. So I'm here with all of you guys today. I'm going to be discussing Hazelcast's Viridian cloud offering in the context of deploying and building efficient microservices in the cloud. But before I do that, just a quick question. Anyone who has used Hazelcast in their career, raise your hand. Okay, we've 2, 3, okay. Raise your hand if you've used any other in-memory data grid solution in your career. That would be Pivotal Gemfire, Apache Ignite, GridGain. Okay, got it. IMDG users. Okay, GridGain, Red Hat Infinispan. Any Infinispan users? Okay. So yeah, I will definitely need to retain the part of my talk where I explain sort of what an in-memory data grid is. So with that said, let's go ahead and get started. So the outline of my talk is we'll start out with Hazelcast and microservices and their long history together from the dawn of sort of service-oriented architecture around 2010 to 2012. Hazelcast was founded as an open source project in 2012 and only later became a commercial entity. As part of that, I'll describe the Hazelcast platform, which has evolved significantly over the 10 years of its existence. I'll then give some practical examples about how Hazelcast platform has enabled traditional microservices deployments. And sort of by traditional, I mean people who are using on-prem deployments or bare metal in large enterprises. Give a specific example from Capital One Bank. And then we'll talk a little bit about the features in Hazelcast and how those move to the cloud with Hazelcast Viridian. And also how you can sign up for a Viridian managed service account and hopefully tie it into your own applications and use Hazelcast to help you build more compelling microservice endpoints in a cloud environment. So with that said, let's go ahead and continue. So the Hazelcast platform began 10 years ago as an in-memory data grid. An in-memory data grid is a relatively common piece of enterprise middleware, but not one that a lot of people have heard of unless they work in certain areas like finance and IoT that require very low latencies. We're not the only one in existence. There's also Oracle Coherence. There's GridGain and its open source flavor, Apache Ignite. There's Red Hat's Infinispan. There's Pivotal's Gemfire. But we are, according to dbmetrics.com, the largest deployed in-memory data grid in the world. So an in-memory data grid is basically a fault-tolerant in-memory object store. It's basically a NoSQL database that keeps all of its data in RAM. It is, by necessity, a clustered solution. It would have to be, right? Because as we all know, memory is volatile, right? A server goes down, you would lose data, right? So the point that I'm trying to get at by saying it's by necessity a clustered solution is that in building this out as a data grid, we've already had to think about things like cluster member management, failure detection of cluster members via different mechanisms. You can use standard TCP timeouts, or if you want more aggressive failure detection, we have an ICMP failure detector, which obviously, doesn't require an open TCP connection, right? Because it runs on UDP. And at that point, you can get, your failure detection timeouts down to a handful of seconds. One of the other things that comes with having been a clustered solution from the beginning is the ability to do an elastic horizontal scale out. If you want to expand cluster capacity, you just add more nodes. The data is sitting hot and ready in memory, and it's very easy to rebalance data. And that is to say, to achieve an approximately uniform distribution of data throughout the cluster. There's a consistent hash algorithm that's used that's relatively complex, and it's an implementation detail, but all you need to know is that if you add another node, your data will be rebalanced in a relatively uniform way. And a lot of this just came out of the reality of dealing with memory as the primary storage medium instead of disk. But it becomes really important when we get into, I bring these points up just to say when we get into deploying in the cloud, when you look at a lot of solutions other than Hazelcast for doing similar stuff, they have a much bigger footprint as a clustered solution. So if you think about a product like Apache Spark, right, which came out of the Hadoop ecosystem, it has all of that Hadoop ecosystem stuff that goes along with it, right? So it uses Zookeeper for cluster management, right? It uses HDFS for intermediate storage. None of that's necessary in Hazelcast as we built our entire cluster fabric and clustering mechanisms from the ground up very early in the development of the product. It's not very hard once you understand an in-memory data grid to understand the beauty of in-memory data grids in a microservices world, right? I mean, microservices are inherently stateless, as we all know. So, we are looking at a situation here where, there's a request that comes in through a load balancer, and it happens to be routed to service instance 1. And the request says, it's an HTTP post request. It's got JSON payload in there, and it's HTTP request body, and it says, apply this transaction to this customer. Well, that's great, but where does the transaction and the customer, where do they actually live, right? I mean, by definition, these services here in this tier, your service tier is stateless, right? And that's the whole point of statelessness in the service tier is the load balancer can route the request anywhere. I mean, here in this example, right, we're routing to the other service instance. You can also elastically expand the number of service instances, right? But we all know this. This is sort of the core of microservices design principles. So you need an externalized state store. And you could use a relational database. These standard Java Spring Boot services, this is a Java conference, so I'm assuming we're using Spring Boot, not Nginx, say, to implement our microservices. We could have a JDBC connection coming off of this guy, and it could go, and it could there could be I'll try to draw one of the Oracle cylinders here. Sorry, I'm not an artist, so this is that's a relational database. Point being that you could touch your customer and transaction state that way, right? And a lot of services are actually built this way. What are the problems that you immediately run into, right? One of them is scalability. Relational databases generally scale vertically. You want more capacity, you need a bigger machine. That doesn't work very well when the entire point of microservices is, as your load increases, expand the number of service instances you have. You can see if you were an online retailer, the difference in service call volume to your inventory processing services might be 100 times or 1,000 times higher on Black Friday compared to an average Tuesday in the middle of March, right? If you're talking several orders of magnitude difference, you want horizontal scale out to deal with that from a capacity standpoint. You can't do that, with a traditional relational database. You do have NoSQL databases that are horizontally scalable, and are clustered solutions. Cassandra is a clustered solution. They're disk-based, however, right? So if you want low latency and data to be kept hot and ready in memory, which means it's not only easy to access and fast to access, by which I mean sub-millisecond access time, it's also very easy to put on the wire for the network to rebalance it, right? You don't have to read it into memory and then put it on the wire for the NIC. So the point that I'm getting at here is that in-memory data grids, one of their chief use cases throughout their entire existence has been to operate as an externalized state store for microservices, a place to keep the customer and transaction objects, the actual business objects that your services are going to apply logic to. So think about any kind of service that we have, right? Whether you're making an HTTP post request to a RESTful microservice endpoint, whether you're making a gRPC call, or if you're in the cloud, which we're going to get to in just a few moments, you might even be having serverless functions, right? Like AWS Lambda. So the basic idea is you want to apply behavior or mutations to state, and that state has to live somewhere. And in-memory data grids have become, in very high-volume organizations, a standard piece of middleware to be backing state stores for rich ecosystems of microservice endpoints. So if you guys aren't using an in-memory data grid to externalize state for your service endpoints, I would highly recommend doing so. I'll talk a little bit about why I think Hazelcast is the best choice among IMDGs out there, because Hazelcast does a little more than just being an in-memory data grid. So with that said, I think we understand the basic idea of IMDGs and microservices. The last thing I wanted to say is that the IMDG solutions, including Hazelcast, all allow you to write through or write behind the mutations to these business objects to a system of record, and to have pluggable support for object relational mapping of various kinds, whether that's Hibernate or custom or whatever. We can see that this is, definitely a better way to do state storage for our microservices. If we want a bigger cluster, that's no problem. We can scale from 3 nodes to 7 nodes to whatever in a matter of seconds. One of the questions that I often get asked is, what's the difference between an in-memory data grid and a simple cache like Redis? The answer is that Redis is just that. It's a key value store. It has a queue and some other stuff as well, but that's pretty much it. And, unless you know the primary key of something, by which I mean the key value key, it's actually very difficult to get data out of something like Redis, or Memcached, or any of those products that are simple caches, right? In-memory data grids allow a number of very compelling features. You can execute code that's co-located with data, and you can have robust query APIs that support SQL. We support SQL queries by creating virtual tables, even though what you're going to store in the in-memory object store is an object. The fields of that object can be treated as virtual columns in a virtual table and indexed appropriately for, very rapid indexed queries. I will talk about, if I'll just switch to my web browser real quick here, and just share, if you just Google Capital One Hazelcast, this is one of our customers that has written significantly about their use of IMDGs. They had a great article in Medium as part of the Capital One Tech blog. The ABCs of building IMDGs with Hazelcast, and so they actually use Hazelcast for their fraud detection service endpoints. So think about the ability to query every credit card transaction that you've made in the last year, to compare that with a new transaction that's come in, to execute as part of asking, think of the service request response here from a microservice design standpoint. The service request is, I have a transaction, tell me if it's potentially fraudulent. The response is, this is a confidence score that we're 76% confident that this transaction is non-fraudulent. So they do all of this over a year of previous transactions to make sure that your current transaction is in the ballpark, and they use several stochastic ML algorithms to do it. But The point is that they have less than 100 milliseconds to do so in the event of a challenge response to credit card authorization when you do a swipe. So the point that I'm making is there is no other way other than in-memory solutions to get latency like that. And that's something that we take very seriously at Hazelcast as a core design principle, is ultra-low latency, high throughput, high performance solutions. So it's also something, by the way, that you could not implement with a simple cache, right? Because simple caches cannot execute code on top of the data in a co-located fashion, which is you could see as sort of like a stored procedure in a database. Nor can simple caches do robust queries that you would need to get a cross-sectional view of customer behavior. So that's where the Hazelcast platform began, and that Capital One blog was from 2019, which is now 3 years ago. So the Hazelcast platform today has evolved into a platform that combines two distinct elements. There is fast data management, or I would call a fast operational data store. This was the IMDG API. This was the original Hazelcast product in a nutshell. On top of the IMDG API, we added what has become known as the Jet API. And the Jet API is an API for expressing streaming computations. I'll actually show you some Jet code in just a moment. It's a fluent declarative API. And you can think of the Jet streaming compute engine as something analogous to Spark or Flink. It could be run on live continuous business events, or it can be run in batch mode. And the two APIs are within the same runtime, and they're coupled together. So if you're doing something like, let's say you're listening to a Kafka topic, and a new event comes in, so you've got a business event that's arrived, and it's basically a UUID for a network device. Let's say you're in an IoT type scenario where you're monitoring your routers and switches in your network, and a UUID for a network device comes in, and you want to fill that into an actual record that has semantically meaningful information about the device, like who manufactured it. Was it Cisco? Was it Broadcom? What model is it? What's its firmware revision? Because that could be a big issue if you need to patch firmware. So one of the notions that we have in the streaming engine is this notion of data combination, which is one of the forms of combination is enrichment, which is what I was just getting at, which is you can query the in-memory data grid layer during a stream computation, and you're doing so within the same cluster. So one of the things that you'll see in deployments of Spark and Flink when people are doing pretty serious heavy lifting and trying to do analytical failure prediction of, is this network switch about to fail, if people are using Spark or Flink, they often need some kind of external store in which to store state for enrichment, right? And in Hazelcast, that's all within the same runtime. And the runtime is just a Java application. It's like a 40 megabyte jar file, basically. And we do all of the other stuff that you would expect from a streaming API. I mean, your filter map, flat map, various forms of aggregations, rolling windows, that sort of thing. We also have a machine learning inference runner. And the purpose of this is when we talk to our customers, when we introduce the streaming API, we found that a lot of people wanted to implement ML in their organization. The most natural way to do it was as part of stream or batch jobs where you already were performing streaming analytics. But there was a disconnect, right, in the sense that most actual data engineering pipelines are built in Java, or in some cases C++ for very high performance. Whereas data scientists tend to work a lot in Python. And this is a Java conference, obviously, but I am going to talk a little bit about our inference runner and how it bridges this divide between data scientists and data engineers. Obviously, the purpose of doing ML inference is just so that you have actionable context that that can come out of this, right? I mean, if you see an IoT device that's about to fail, issue an alert, right? The one thing that I was going to say is that there's a very robust ecosystem around this product. Do I need to stop my show real quick here? So if you go, for instance, to hazelcast.com/hub, you might be interested in ways to kind of prime your streaming pipeline. So one of the things that you might want to do is change data capture from MySQL. So if I just do a search for MySQL CDC, oh wow, there it goes, the MySQL CDC connector. Let's say I want to connect to Kafka. Oh, I've got quite a few Kafka connectors, actually. Legacy JMS. Got a connector for that. ActiveMQ, we're good to go. And to step back a second, as nice as all of the streaming analytics stuff is and talking about machine learning, one of the other things that I admit as a developer is that, like, I don't do that much ML stuff on a regular basis. But one of the things I do a lot of is data transformation and moving data from one place to another and converting its format, basically ETL type operations. So when we talk about streaming compute, you don't necessarily just have to think about streaming analytics. I mean, that enrichment that I talked about earlier, where you go from a UUID to a record, that could be really valuable as part of an ETL process. So one of the things that has sort of come out of this fusing of an in-memory data grid, which also now supports the ability to spill over to SSDs, so you can have more data than you have available memory, with a stream processing engine, is this notion of a digital integration hub, right? So this is, you're taking data from a bunch of places, change data capture from databases, IoT devices, right? You're using the stream processing engine to move this data in to the operational data store that's not just in memory anymore, but we'll say it's memory first or memory centric, very low latency access. And you can a lot of customers kind of use this as what I would call a materialized view store, or what Gartner and Forrester call it in their reports is a digital integration hub. So, you basically want to mash up real-time data that's coming in with contextual master or reference data that's stored in the grid, right? These could be for 360-degree data views, customer 360 type stuff, right, where you have customer click streams and that sort of thing, and you want to combine that with historical data about customer behavior, and then try to determine whether they're going to abandon their shopping cart or not. That's all possible, and you can have applications that connect to this, and this digital integration hub once you have it. And one of the most powerful things you can do with the digital integration hub is stick it behind a microservice endpoint, which becomes a way of querying it, right? So Hazelcast handles the combination of data from Kafka, IoT devices via MQTT, change data capture events from traditional relational databases. So all of these business events are happening. You're capturing them and you're mixing them with sort of contextual or historical data, and in doing so, you're allowing your microservices to do a great deal more than they have in the past, and to see a much richer view of your data, and to make querying through service endpoints a richer experience for your consumers. So with that said, I don't want to go over here. So we'll move on. past some of the boilerplate slides that I have. I think we covered the fact that the Hazelcast platform unifies data at rest via the IMDG API and data in motion via the streaming API. The streaming API gets a lot of discussion about doing ML execution, and the one thing that I did want to point out that we have figured out how to do in Hazelcast is to execute Python code in a massively parallel way. So Hazelcast itself runs as a JVM process. Knowing the constraint that you have with Python, that Python is basically a single-threaded language, right? It has this notion of a single interpreter lock. We can, for instance, spin up as many CPython VMs. These are not Jython, these are actual CPython VMs, as you have available CPU cores. And so if you've got a 2-core machine, you'll have 2 CPython VM instances. If you've got a 4-core machine, you'll have 4 CPython VM instances. I can actually show you an interesting example of this in my IDE here. So this is actually a common problem that happens to us Java developers. You get this, which is a bunch of Python code that a data scientist used, in this case, to develop a movie recommendation engine. It takes its input from input.txt and writes its output to recommendations.txt. So was fine, I said I liked Top Gun, but let's say I instead liked Toy Story, right? I'm going to go ahead and execute this, and the most interesting thing that you'll see here is that this is a Java process, but you'll see all of this Python initialization code here, right? Do you see we're actually running pip, the Python package manager? When the Hazelcast cluster starts, it will actually load and create an entire Python virtual environment, and it will create as many instances as it needs to execute a Python ML model. It'll build wheels. How many of you guys are Python developers at all? Raise your hand. Yeah, so you're vaguely familiar with wheels as compiled artifacts, right? So yeah, this is going to take a second to run because we have to prepare the Python environment. Obviously, in a real-world scenario, you would not be waiting 1.5 minutes for this to happen because I would already have my Hazelcast cluster running. But what I'm actually doing here is creating a Hazelcast cluster locally on my laptop, and it's now uploading the Python resources that I need, including quite a bit of ML libraries. Like if you look at my Python imports here, I've got a like of scikit-learn, stuff. So yeah, while that runs in the background, and we're going to spin up 10 CPython VMs because I have a 10-core machine, that's the ML execution part of Hazelcast. And if you're in a situation where you want to operationalize ML, one of the simplest things that you can do is, let's imagine that we're working for, big old streaming service or BOSS, B-O-S-S, and someone wants to watch something on their tablet device, and they've said that they like Toy Story. The kind of cool thing is you can abstract that entire process behind a typical Spring Boot endpoint. I mean, you make a REST call, the HTTP request body is Toy Story. The Hazelcast JVM will execute that Python in a massively parallel way. You get your results back. One thing that I would point out is that we have a series of benchmarks comparing us to other streaming products, including Spark and Flink, and we were able to do 1 billion transactions per second with our 99th percentile latency under 30 milliseconds. That said, this did require 45 nodes, which is a pretty big cluster. Let's go back and check out our recommendations. Did it populate them? Yes, it did. So here you see the IMDb movie ID, the movie title, and here you see the confidence score. And what we've gotten is Aladdin is, of course, another Disney movie, as is Balto, as is Hercules. 101 Dalmatians makes sense, the classic kids film. So yeah, the recommendation engine worked vis-a-vis Toy Story. So there we go. And that was Python code being completely managed from inside of a JVM. That said, we've only got a few minutes left, so let's do the cloud, right? You like Hazelcast, you like what you've seen, you like stream processing, you like Python execution, you want to just take your Python code, use our jar packaging tool, upload it into the cloud. You want to use the Hazelcast InMemory data store to externalize state in your microservices. We do cloud native very well, right? We don't require, being that we were built from the ground up with our own sort of clustering engine built in and for failure detection and all of that, as I mentioned earlier, we don't require all of this complex stuff that something like Spark does, where you have master nodes and worker nodes. And then you have Zookeeper to keep track of what kind of nodes you have. And then you have HDFS for intermediate storage. I mean, if you've ever deployed Spark or like a Cloudera solution, there's a lot to deploy. So because of our simplicity, it was very easy for us to build a fully managed cloud solution called Hazelcast Viridian. The fully managed cloud solution is multi-availability zone. So, you lose one AZ, you don't lose your data. You can do even multi-region via our WAN replication solution. One of the cool things is we support multi-cloud. We're available on all three major cloud platforms, AWS, Azure, and GCP. And we can do replication between them. So if you don't want to get locked in to a particular cloud provider, it's a very powerful idea. We can also use our WAN replication feature to replicate from on-prem into the cloud. Viridian is fully managed, it's easy to use, it's highly scalable, it's Hazelcast just running on top of Kubernetes plus Docker, and given what you've seen about how easy clustering is in Hazelcast, I'm sure that you can see that this is a marriage made in heaven. We're SOC 2 and ISO 27001 certified, so if those certifications are important, because we'll be holding your data potentially, that's all available. The sort of technical use cases for this, I probably don't even need to spend that much time on it. Here is externalized state store for microservices. Here is externalized state store for serverless tasks, where you have, a function as a service, be that, AWS Lambda or something like that, and you need to manage state. Autoscaling. One of the coolest features of the product is that given the fact that it runs on Kubernetes, you can grow and shrink the cluster based on a number of monitored cluster metrics. Autoscaling is triggered when various min-max values are exceeded. These can be heap memory usage, off-heap memory usage, CPU use, number of clients, etc., garbage collection pause statistics. You can also manually scale with a single click when desired. You want to go ahead and give it a shot. It's pretty straightforward. Let's go to hazelcast.com and say that I want to start coding now in Hazelcast Viridian serverless, and sign in with my Google account. And yeah, you can see I have a serverless cluster here deployed in AWS US West region. The other thing that I'll say is that the documentation is actually great. So if you want to click on the Learn, you can see things like building cluster-side modules, how multi-factor authentication works, how you connect remotely to Hazelcast clusters, potentially from function as a service endpoint. So I've gone over time, I believe, by about 5 minutes. So my apologies, but that's pretty much all I got. I'll take questions if anyone has one. Go ahead, please. Yeah.
Is this having a read and write consistency?
Yes. Yeah. It's. I mean, you can actually achieve ACID level consistency, provided you use the Transactions API. And we also have a CP subsystem that uses the Raft consensus algorithm. So yeah, the level of consistency you can achieve is extremely high, even though it is an in-memory system. But it's fungible. You can trade off consistency if you want higher performance. Any other questions?
So what happens in case of disaster recovery?
Well, I mean, you can turn persistence on, for one, which means, and you can use fsync level persistence, which means that everything that's in memory is going to be mirrored to disk, right? That'll save you in the event of a power failure. But that's not going to help you if your cloud provider's region is down for a while, which is why we would recommend using multiple regions with one cluster in each region, and then enabling our WAN replication feature, which is an eventually consistent batching replication feature that's designed for slower WAN links between regions, and that's going to give you, robustness even if, you need to switch to a completely different region or a completely different data center if you're in an on-prem scenario. Yep. Okay. Thank you, guys.